Imagine taking a photograph of the universe. Not just a galaxy, not just a cluster of stars, but the entire observable cosmos spread out before you like a map. What would you see? In 2005, astronomers did exactly that. They compiled data from hundreds of thousands of galaxies, creating the most comprehensive map of the universe ever made. What they discovered shouldn't exist according to any theory of how the universe formed. They found a pattern, a structure so vast, so impossibly organized, that it spans hundreds of millions of light years. Galaxies aren't scattered randomly through space. They're connected, woven together like neurons in a cosmic brain, threaded along invisible filaments that form the largest structures ever observed in nature. The universe has a skeleton, and it's alive with mysteries. This structure defies our understanding of physics. It challenges the timeline of cosmic evolution. It suggests forces we haven't yet discovered, pulling on the fabric of reality itself. Today, we journey through evidence that challenges everything we thought we knew about how the universe organizes itself. We'll follow invisible threads that connect galaxy to galaxy across the void. We'll explore the immense darkness between them, and we'll confront the possibility that the pattern we see might not be random at all. In 1989, Margaret Geller and John Hutchcroft at the Harvard-Smithsonian Center for Astrophysics were conducting a routine survey. They were mapping galaxies in a thin slice of the sky, measuring their distances from Earth. The project was called the CFA Redshift Survey, and nobody expected it to reveal anything revolutionary. But as the data accumulated, Geller noticed something extraordinary. The galaxies weren't distributed evenly through space. They formed a pattern, a wall. An impossibly large structure of galaxies arranged in a thin sheet stretching 500 million light-years across space. They called it the Great Wall, and it shouldn't exist. According to prevailing theory, the universe began with near-perfect uniformity. The Big Bang should have scattered matter relatively evenly in all directions. Gravity would pull it together over time, forming stars, then galaxies, then clusters of galaxies. But this process takes time, billions of years. The Great Wall suggested something else, something organized matter on scales so vast that gravity alone couldn't explain it, not in the time the universe had existed. Margaret Geller described her reaction simply: it was a surprise that something so large could exist. But the Great Wall was just the beginning. Mapping the invisible. To understand what came next, you need to understand what we can't see. Between galaxies lies the void, empty space. Or so we thought. In the 1970s, astronomers realized that galaxies were spinning too fast. The stars on their outer edges should fly off into space like water droplets flung from a spinning wheel. But they don't. Something invisible is holding them together. Something with mass, something with gravity. They called it dark matter. We can't see it. It doesn't emit light or absorb light. It doesn't interact with electromagnetic radiation at all. But it has mass. And mass has gravity, and gravity we can measure. The mathematics suggested something staggering. For every kilogram of normal matter in the universe, every atom in every star, every planet, every dust particle, there are 5 kilograms of dark matter. The universe is 85% invisible. But here's where it gets strange. If dark matter dominates the universe's mass, then dark matter must dominate its structure. The visible universe, every star we see, every galaxy we photograph, is just a trace element, a signature of something much larger lurking beneath. In 1996, cosmologists began running computer simulations. They programmed in the Big Bang, the expansion of space, the gravitational effects of both normal and dark matter. Then they let the simulation run forward 13.8 billion years to see what structure would emerge. The results stopped them. The web revealed. The simulation showed filaments, long, thread-like structures of dark matter stretching across the cosmos. Where these filaments intersected, matter pooled into dense knots. Along the threads, galaxies formed, like dewdrops on a spider's web. Between the filaments lay vast, empty voids. The pattern looked organic, almost biological, like neural connections in a brain or mycelium threads in a forest floor. This was the cosmic web, and it predicted exactly what Geller and Hutchcroft had observed: vast walls and filaments of galaxies separated by enormous voids. But simulations are just mathematics. The real question was, does this structure actually exist? In 2003, two teams of astronomers conducted the most ambitious galaxy surveys ever attempted. The Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey mapped the positions of over 1 million galaxies. And when they plotted the results, the pattern was unmistakable. The cosmic web was real. Galaxies trace out filaments hundreds of millions of light years long, connecting across the universe like highways of matter. At the intersections sit massive galaxy clusters containing thousands of galaxies. Between the filaments lie cosmic voids, regions nearly empty of galaxies, some spanning 500 million light-years across. The largest structure yet discovered, the Hercules Corona Borealis Great Wall, stretches 10 billion light-years across space. That's nearly 10% of the observable universe's diameter. A structure so large that light takes 10 billion years to cross. But the evidence forces us to confront an uncomfortable possibility. This structure formed far too quickly, and it's far too organized. Something about our understanding of cosmic evolution is incomplete.
For decades, astronomers faced an embarrassing problem. They could calculate how much normal matter, baryonic matter, atoms and molecules, should exist in the universe. The math is straightforward, predicted by Big Bang nucleosynthesis. But when they counted up all the stars, all the gas clouds, all the dust, all the planets, everything they could observe, they came up short. 40% of the universe's normal matter was missing. In 2017, astronomers found it hiding in the cosmic web. Using the Chandra X-ray Observatory, researchers detected a faint X-ray glow between galaxies. This radiation came from gas heated to millions of degrees, matter so hot and diffuse it had evaded detection for decades. This warm-hot intergalactic medium, or WIM, threads through the cosmic web's filaments. The missing matter had been there all along, invisible in the darkness between galaxies. Approximately 10 to 40 billion solar masses of gas flows through each filament, connecting the visible islands of galaxies like bridges across the void. The discovery confirmed predictions, but it raised new questions. What heated this gas to millions of degrees? What keeps it suspended in these filaments? The energy requirements are staggering. In March 2012, astronomers using the Hubble Space Telescope observed something remarkable: a filament of dark matter captured directly through gravitational lensing. When light from distant galaxies passes near massive objects, the gravity bends space-time itself. The light curves around the mass, creating distortions, like looking through wavy glass. By analyzing these distortions, astronomers can map the invisible matter causing them. Between two galaxy clusters 2.7 billion light-years away, Hubble detected a bridge, a filament of dark matter connecting the clusters exactly as the cosmic web theory predicted. The filament contained enough mass to equal 90 trillion suns, yet it was completely invisible except for its gravitational signature. Jörg Dietrich, lead researcher at the University of Munich, stated, "This is the first time we've been able to measure the shape of the dark matter distribution within a cosmic web filament." The discovery provided direct observational evidence. The web isn't just an artifact of galaxy distribution, it's a physical structure of dark matter spanning the cosmos. But this represents just one piece of a much larger puzzle. In 2014, researchers analyzing data from the Sloan Digital Sky Survey noticed something that shouldn't be possible. Galaxies separated by hundreds of millions of light-years were rotating in the same direction. Their spin axes were aligned with the cosmic web filaments they resided in. Galaxies in filaments pointed along the filament. Galaxies in walls lay flat against the wall plane. The correlation was too strong to be coincidental. Across distances where no force should connect them, galaxies remembered their orientation from the cosmic web's formation. Dr. Joon-Hoon Lee at Seoul National University, investigating this phenomenon, found the alignment extended even further. Galaxy clusters themselves show preferential orientation relative to the surrounding large-scale structure. The alignment persists across scales, from individual galaxies to the largest structures in the universe. This suggests the cosmic web's formation imprinted patterns on everything within it. Like iron filings aligning with a magnetic field, the universe's matter follows invisible lines of force. Then there's the motion. Galaxies don't just sit in the cosmic web, they flow through it. The Virgo supercluster, the massive structure containing our Milky Way galaxy, is moving towards something. In 1986, astronomers detected this flow, hundreds of galaxies streaming in the same direction at 600 kilometers per second. The Great Attractor, they called the destination, a gravitational anomaly pulling entire galaxy clusters toward it. But in 2014, astronomers discovered something larger, the Laniakea supercluster, a structure encompassing 100,000 galaxies, including our own, all of it flowing along cosmic web filaments like water through pipes. These flows reveal the web's dynamic nature. Matter slides along filaments toward nodes. Galaxies migrate from voids toward walls. The structure isn't static, it's active, growing, evolving. Measuring these velocities across millions of galaxies has revealed the invisible rivers of dark matter channeling visible matter through cosmic corridors.
In 2004, NASA's WEMAP satellite was mapping the cosmic microwave background, the afterglow of the Big Bang. This radiation fills the universe uniformly, showing tiny temperature variations that represent density fluctuations in the early universe, except in one region. There, astronomers found a void in the CMB radiation, the cold spot, a region 1.8 billion light-years across, where the temperature is 70 microkelvins cooler than the surrounding regions. This shouldn't exist according to standard cosmology. The early universe was too uniform for such a large cold region to form, yet there it is. In 2015, researchers confirmed a correlation. The cold spot aligns with a supervoid, an enormous empty region in the cosmic web, the largest void ever discovered. The Eridanus supervoid contains 10,000 fewer galaxies than expected and spans 1.8 billion light-years. But here's the problem. Even this supervoid isn't large enough to explain the cold spot entirely. Something else is going on. Some astronomers have suggested we're seeing the signature of cosmic web formation happening during the universe's earliest moments, patterns frozen into reality itself. The most remarkable discovery involves the relationship between voids. Cosmic voids aren't truly empty. They contain some galaxies, but these galaxies are different, smaller, less active, evolving more slowly than their counterparts in filaments. In 2016, astronomers discovered why. Using the Keck Observatory and others, they measured how fast galaxies and voids are forming new stars. The rate is lower, much lower. Galaxies and voids are being starved of gas. The cosmic web channels matter from voids into filaments. Over billions of years, the voids have been drained, their gas pulled away by the gravitational highways surrounding them. The voids aren't just empty, they're actively being emptied. This creates a feedback loop. As matter drains from voids, the filaments grow denser. This increased density pulls harder on remaining matter, accelerating the drainage. The rich get richer, the empty grows emptier. But measuring void sizes over time has revealed something unexpected. The voids are expanding faster than the universe's expansion rate alone would predict. Something is pushing them outward from within. This brings us to the universe's strangest component, dark energy. In 1998, astronomers studying distant supernovae discovered the universe's expansion is accelerating. Something is pushing space itself apart, overcoming gravity's pull. This mysterious force comprises 68% of the universe's total energy content. Dark energy appears uniform throughout space, but its effects are most visible in cosmic voids. Where matter density is low, dark energy dominates. The voids expand, pushing filaments apart. Recent research from the Dark Energy Survey suggests the cosmic web's structure might be key to understanding dark energy. By mapping how the web has evolved over billions of years, astronomers can measure dark energy's strength and how it's changed over time. In 2018, analysis of 26 million galaxies revealed the cosmic web has been stretching, its filaments growing longer and thinner. The voids have grown by 20% over the past 7 billion years. This rate of growth constrains dark energy's properties. The evidence extends beyond mere structure into the realm of cosmic evolution itself. The web isn't just a map of where galaxies are, it's a chronicle of how the universe has developed, shaped by the interplay of dark matter, dark energy, and the visible matter we can see. Let's reconstruct how the cosmic web formed, starting from the beginning. 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before this moment, matter and radiation were locked together in a hot plasma. After this moment, called recombination, light could travel freely through space for the first time. But the universe wasn't perfectly smooth. Tiny quantum fluctuations from the Big Bang's first moments had been stretched across space by cosmic inflation. These variations in density were minuscule, 1 part in 100,000, but they were enough. Gravity began pulling matter toward these slightly denser regions. Dark matter, unaffected by radiation pressure, collapsed first. It formed halos, gravitational wells where normal matter would eventually collect. By 200 million years after the Big Bang, the first stars ignited. By 500 million years, small galaxies formed. But the cosmic web's structure was already in place. Dark matter had formed the scaffolding. Visible matter simply filled it in. This hierarchical structure formation continues today. Small halos merge to form larger ones. Galaxies slide along filaments toward nodes. Clusters grow more massive. The web's architecture remains, but everything within it is dynamic.
This forces us to reconsider fundamental assumptions about how structure forms in the universe. The standard model, lambda cold dark matter, predicts the cosmic web's basic features remarkably well. It accounts for the filamentary structure, the voids, the hierarchical growth. But it struggles with the details. The Hubble tension, for instance. Different methods of measuring the universe's expansion rate yield different results. Measurements using the cosmic microwave background suggest one value. Measurements using distant supernovae suggest another. The discrepancy is statistically significant and unresolved. Some cosmologists propose modifications to dark energy to explain this tension. Others suggest we're missing a component in our models. Perhaps dark matter interacts with itself more than we thought. Maybe there are additional forces operating on cosmic scales. Dr. Carlos Frank at Durham University, one of the architects of cosmic web theory, has suggested the resolution might lie in better understanding how baryonic matter, normal matter, affects dark matter halos. The feedback is more complex than simulations initially predicted. Another mystery, the cosmic web formed too quickly. The largest structures we observe required more time to grow than the universe's age allows, unless matter clumped together more efficiently in the early universe than our models predict. What does it mean that the universe is organized into such a vast structure? The cosmic web is self-similar across scales. The pattern you see across billions of light years resembles the pattern you see in galactic neighborhoods. This fractal-like quality suggests fundamental organizing principles at work. Some physicists have noted the resemblance to biological structures. The cosmic web looks like neurons, like fungal networks, like capillaries. This similarity isn't coincidental. It reflects universal principles of how networks form and optimize connections. Does the universe have a memory? The alignment of galaxies with filaments suggests it does. Information about the web's formation is preserved in galaxy orientations, in velocity flows, in the structure itself. Dr. Margaret Geller reflected on her discovery. The universe has structure all the way up. It's not just galaxies and clusters. There's a whole hierarchy we're still mapping. Recent breakthroughs suggest we're entering a golden age of cosmic web astronomy. The Dark Energy Spectroscopic Instrument, or DESI, began full operations in 2021. Over 5 years, it will map 35 million galaxies, creating the most detailed three-dimensional map of the cosmic web ever constructed. Early results have already challenged existing models, showing structure at greater distances than expected. The James Webb Space Telescope, launched in 2021, is observing the universe's earliest epochs. It's detecting galaxies forming just 300 million years after the Big Bang. These observations reveal how quickly the cosmic web's skeleton formed and how early galaxies populated it. In 2023, JWST discovered massive galaxy clusters existing far earlier than theory predicted. These clusters, containing hundreds of galaxies, should have required billions of years to assemble, Yet they existed when the universe was less than 2 billion years old. This discovery reinforces the cosmic web's early formation. The scaffolding must have been in place even earlier than we thought, guiding rapid galaxy formation along predetermined paths. The next generation of cosmic web research will come from multiple fronts. The Vera C. Rubin Observatory, beginning full operations in 2025, will survey the entire visible sky every few nights. Over 10 years, it will generate a movie of the cosmos, showing how the cosmic web evolves in real time. This time-lapse of galactic motion will reveal how matter flows through filaments and how structures merge. The Euclid Space Telescope, launched by the European Space Agency in 2023, is specifically designed to map the cosmic web's dark matter structure. Using gravitational lensing on an unprecedented scale, Euclid will trace dark matter filaments directly, measuring their thickness, density, and evolution. In the 2030s, the Square Kilometer Array will begin operations. This radio telescope, spread across South Africa and Australia, will map neutral hydrogen throughout the universe. Hydrogen traces the warm, hot intergalactic medium threading through cosmic web filaments. SKA will reveal the detailed distribution of baryonic matter in the web. These observations will answer pressing questions. What this means for us extends beyond pure astronomy. Understanding the cosmic web helps explain why galaxies exist at all, why stars formed where they did, why our galaxy, our solar system, our planet exists in this particular corner of the universe. We live in a filament. The local group of galaxies, including the Milky Way, occupies a minor thread in the cosmic tapestry. We're being pulled toward the Virgo cluster, sliding along invisible rails of dark matter. In billions of years, our galaxy will merge with Andromeda, forming a larger elliptical galaxy. Eventually, this combined galaxy will become part of the Virgo cluster itself. But the cosmic web also constrains the future. As dark energy drives cosmic expansion, the web stretches, filaments thin, voids expand. Eventually, in trillions of years, the web will tear apart. Galaxy clusters will become isolated islands in an expanding sea of darkness. Each will lose sight of the others as space expands faster than light can cross it. The cosmic web is temporary, a phase in the universe's evolution. But it's our phase, the era when structure exists, when matter organizes itself into galaxies and stars and planets, when complexity is possible. The most profound implications emerge when we consider the web's role in life itself. Where does life arise in the cosmic web? Not everywhere, perhaps not even in most places. Galaxies and voids are starved of gas. They form fewer stars, fewer planets. They experience fewer supernova explosions spreading heavy elements necessary for rocky planets and biochemistry. Life in voids would be rare if it exists at all. Galaxies at the densest nodes in massive clusters face different challenges. High-velocity collisions strip gas from galaxies. Intense radiation from countless stars floods the environment. Close encounters disturb planetary systems. Life might struggle to persist. But along the filaments, that's the sweet spot. Galaxies receive enough gas to form stars and planets. They're not so crowded that collisions disrupt development. There's enough time for complex chemistry to evolve. Research by Dr. Jamie Ferrero Romero at the University of the Andes suggests the majority of potentially habitable worlds exist in filament galaxies like our own. The cosmic web doesn't just organize matter, it creates the conditions where complexity, chemistry, and perhaps consciousness can emerge. If this is true, then intelligent civilizations in the universe aren't randomly distributed. They follow the web. They concentrate along filaments. Communication between civilizations would most likely occur within the same filament, not across voids. Consider another implication. The cosmic web connects everything. Quantum entanglement, the phenomenon where particles remain connected regardless of distance, has been demonstrated across hundreds of kilometers on Earth. Some physicists speculate these quantum connections might extend to cosmic scales, linking matter across the web's filaments. While direct evidence remains elusive, the theoretical possibility raises profound questions. Could information be shared across cosmic web structures through quantum channels? Could the web itself facilitate correlations we haven't yet detected?
Dr. Jan Maldena's holographic principle suggests information about what happens in a volume of space can be encoded on the boundary of that region. Applied to the cosmic web, this implies the filaments and walls might contain encoded information about the voids they surround. The universe might not just have structure, it might have memory, information storage in the geometric arrangement itself.
Why does the cosmic web exist at all? Why this particular structure? The answer involves the universe's fundamental constants. If dark matter interacted slightly differently with normal matter, the web would look different, or might not form at all. If dark energy were stronger, the universe would have expanded too rapidly for structures to form. If gravity were weaker, matter wouldn't clump. The cosmic web exists because the universe's properties fall within a narrow range allowing structure formation. This is the anthropic principle. We observe these properties because they're necessary for our existence. If they were different, we wouldn't be here to observe anything. But this raises an uncomfortable question. Is our universe special, or is it one of many, each with different properties, and we happen to inhabit one where the cosmic web could form? The multiverse hypothesis suggests countless universes exist, each with different physical laws. Most would be sterile, either collapsing instantly, expanding too rapidly for structure formation, or lacking the forces necessary for complexity. Our universe, with its cosmic web, represents a rare case where matter can organize, complexity can emerge, and observers can arise to contemplate their origins. But we can't test this hypothesis. We can only observe our universe. The cosmic web is our only data point. What we can say is this. The web's existence depends on exquisite fine-tuning of multiple properties: the density of dark matter, the strength of dark energy, the initial quantum fluctuations that seeded structure formation. Change any of these by small amounts, and the web dissolves. We are products of the cosmic web, made from matter that flowed through its filaments, born in a galaxy shaped by its forces, existing in the brief cosmic moment when structure persists. We began by asking what the universe looks like when photographed as a whole. The answer challenges everything. The cosmos isn't chaos. It's organized into the largest structure we've ever observed, a web of dark matter spanning billions of light years, connecting everything that exists into a single vast network. We've journeyed through the evidence: the missing baryons found hiding in filaments, the gravitational lensing revealing dark matter bridges, the alignment of galaxies with the web's structure, the flows of matter along cosmic highways, the voids expanding under dark energy's push. We've learned the web formed early, perhaps too early according to standard models. We've seen how it channels matter, creating environments where galaxies form and evolve. We've discovered our place within it, a small galaxy in a modest filament, flowing toward an inevitable merger billions of years hence. The current scientific consensus holds that the cosmic web is real, fundamentally important, and still mysterious. We understand its basic formation. We can simulate its growth. But questions remain. How did it form so quickly? What role does it play in dark energy's effects? Does it constrain where life can arise? Is it unique to our universe, or a general feature of cosmic evolution? These questions drive current research. Each new telescope, each deeper survey, each better simulation reveals more detail. The web's story is still being written. But perhaps the most profound insight is this: the universe at its largest scales resembles the universe at its smallest. Networks forming, connections optimizing, information flowing through structured pathways. From quantum fields to cosmic filaments, nature builds using similar principles. The cosmic web is reality's hidden architecture. It's the scaffold upon which everything we know exists. It's the map showing where we've been and where we're going. It's proof that the universe, for all its vast emptiness, is fundamentally connected. You are made of atoms forged in stars, moved along cosmic filaments, collected in galaxies shaped by invisible forces. You are not separate from the cosmic web, you are part of it. The universe is vast. The mysteries are endless. The journey continues.